Hello everybody and welcome to the beginning of section 14.6. We are looking at page 48 in the workbook, and in this section we will be talking about the chain rule, and that is a rule that you undoubtedly remember hearing about in Calculus 1. We're going to talk about its extension to multivariables. Okay, so I think the best way to illustrate the concept is to start off just with an example. Let's read this together. So we've got a function capital T equals f of xy. Capital T is a temperature, and they don't give us units, so why don't we just make up some units, degrees Fahrenheit. Okay, at the point xy in the plane, and we'll let x and y represent the positions, okay, of our particle, and we'll maybe think about distance in meters. Again, they don't give us specific units. Okay, and then they do tell us that t is in seconds. Okay, and assuming that f, g, and h are all differentiable, we would like to derive a formula for dt dt. Okay, notice that that's the rate of change of temperature with respect to time. Okay, and I'd like to start this discussion just with a diagram. Okay, so basically we've got a particle that's moving around in the xy plane. We don't know exactly where, but you could maybe picture it just moving along a path. Okay, and the variables that you see in the problem, the t, the x, and the y, all have something to do with this picture. So let's start by just mapping out the functions that we have. There's temperature, and that's a function of x and y, our position in the plane. And then we've got x and y themselves, our position, and those are functions of time. So if you're wondering why we're bringing the chain rule into this discussion, this is kind of why. We've got a function within a function, so to speak. T, temperature, is a function of x and y, but then x and y are also functions of another variable. We've got kind of a nesting effect going on. Okay, well again, what they want us to do here is to derive a formula for the rate of change of temperature with respect to time. Let's see if we can do that below here. Okay, and we're going to start with a formula from section 14.3 that looks like this. dt is partial t partial x dx plus partial t partial y dy. Okay, this is the formula for what's known as the differential. Okay, and it's a way of just estimating the approximate change in temperature. That's the dt d big T that you see on the left-hand side of the equation. Okay, what we're actually after though is a derivative. Okay, so to get that derivative, we're going to take this formula that we wrote down and just divide both sides by d little t. And if we do that, on the left-hand side, we got to do it on the right-hand side as well. And so the formula is going to turn into this. And the formula that we just wrote down is what's known as the chain rule. For d big T, d little t. Okay, and we're going to say a few things about this formula, make a few observations. First of all, I'd like to do kind of a unit analysis here if we could. Okay, so kind of working our way down the formula from left to right. If we start with partial t partial x, what would the units of that derivative be? Well, we've got temperature in the top and x in the bottom, so we would have degrees Fahrenheit per whatever unit we're measuring distance in. Let's just say meters, even though they didn't give us units in the problem. Okay, and we're multiplying that by dx dt. What units would that have? Okay, well there, x has units of meters and t has units of seconds, so it's going to be a rate of change in meters per second. And if we go over here, kind of the same thing is going to happen with those two derivatives. Notice that we get some cancellation here. The meters cancel out. And so what are our overall units here then? Well, they're going to be degrees Fahrenheit per second. And notice that those units are consistent with the derivative that we're calculating. That's a rate of change of temperature with respect to time. Okay, oh, and actually, they asked us a question here. I'm going to go ahead and box in this answer just to emphasize that that's the formula that they asked us for. Okay, now we've done everything that they asked us to do in the problem, but I would like to add something to this that I think will be useful in the future. I'm going to need to create a little bit of space here, so let me erase this. What we're going to do is to draw what's called a dependence diagram. Okay, a dependence diagram is a way of kind of representing the various relationships between the variables, and it's a nice way to figure out what this formula is graphically. Okay, let me show you what I mean. So we'll start with temperature at the very top, and we'll ask the question, what variables is temperature a function of? Well, it's a function of x and y. And then look at the x and the y and ask, what are those variables functions of? Those are both functions of time. We can kind of see all of that information up here. And this diagram can be used to arrive at this formula as follows. We're looking for the derivative of temperature with respect to time. So what you do is you go over to your diagram and ask, how many different paths are there from temperature to time in the diagram? Okay, well, let's see. Here's one. We go from temperature to x to t. And notice that our derivatives in the first term correspond to that. We first go from t to x. You can think of that as being the partial t partial x. And then we go from x to t. That's the dx dt. Okay, and that takes care of one of the two paths, the one that takes us from here to here. But then there's another path that takes us from t to t. And if you look at the path there, we're going from t to y. Okay, that's this derivative. And then going from y to t. That's this derivative. Okay, and you can always use a diagram like this to figure out what that chain rule formula is. And we'll use that method in the examples that we do.